set now. We can hear you loud and clear.
All right, now the real test. Can I share my screen? Let's see. All right. Quick check. What does everyone see here? It's a monstrosity. Yes, this is a O'Reilly rendition. I know that. Of course, lately the trend has been Studio Ghibli, but this is an O'Reilly style hybrid of a snake and a bear and a llama. So this is Snek-Bera-Llama. We are going to be trying to quickly one-shot a incredibly intense coding bootcamp here, in which we're going to launch a stablecoin on Berachain, and we're going to be doing so using Vyper. In the event that we're not able to get through the whole thing, don't worry. There's a lot of supplemental resources. It's probably unlikely we're actually going to be able to finish it all, because we like to keep this super interactive. I have the Bera stage chat open, so if you got questions, feel free to drop questions throughout. We are going to get into in just a second, like what you're going to need in terms of the technical side. Just quickly, we first wanted to start by explaining that this is a workshop about Vyper. So I don't know how much experience you guys have with Vyper. Vyper is a very cool programming language. It was started by Vitalik Buterin. He strayed for a while, and it was left to the community, although more recently he has come back. And the idea is that when you are working, of course, with blockchains, especially EVM-compatible blockchains, like pretty much at the end of the day, you're just compiling things down to bytecode. So what language you use, whether it's Solidity or Vyper, is largely a matter of preference. I like Solidity. I use Solidity. I like Vyper a lot. I use Vyper in most of my programming. There's some tasks that Vyper is better for, some tasks that Solidity is better for. There's tons of other good languages. The more languages that are out there, the better the ecosystem is. Vyper is coming about things with a few simple principles. That is aiming to be incredibly secure at the compiler level. So what this basically means is when you're writing in Vyper, they make it tough to write bad code. The language is incredibly simpler. There's a lot of safety features that are built into it that make it, in fact, easier to avoid shooting yourself in the foot. And because it's like nice and clean and readable, it's also incredibly easy to audit given some of the design choices that they've made. So this workshop is focused on how we can work with Vyper. There's a number of major DeFi protocols: Curve, Lido, Aerodrome, Velodrome, Yearn, that use Vyper pretty extensively. So if you're interested in doing any sort of programming in terms of like hardcore DeFi, which of course Berachain tends to see a lot of really incredible hardcore DeFi type apps, knowing some Vyper is a very good thing. What we're trying to do in this unit is we have basically plans to create a lending-based stablecoin in 12 easy steps. And at this point, can we share the links that I sent to you in the Telegram group? There's a couple of parallel things that you can do if you'd like to code along with us. So I'm going to be demonstrating the coding on my screen. If you want, you can just watch the screen. We'll be flipping back and forth between this slide deck and this GitHub repository. If you'd like to follow along the GitHub repository, maybe I can drop it in the links. Let's see if I get banned for dropping this.
This should be good.
Yeah, so there's the GitHub repository. I've created a particular folder for this Berachain tutorial, which I'm going to walk through. Essentially, what this folder contains is a few interesting files we'll be looking at, as well as the goal is to get through all 12 of these. There's 12 checkpoint contracts. So if you are following along in GitHub, within the contracts folder, you'll see 12 different steps. If you get lost, if your code's not coming out clean, if it's not working, you can download the code at any step of the way and catch up. And there's also some links that are included in the GitHub repository, as well as in this deck. If you like to follow along with the deck, occasionally there's a few links, so you can click on this deck and follow the deck at your own pace. A lot of it is just visualization of various Vyper functions. But this 12 steps is going to give us everything we need to know about Vyper. And I'm going to be presenting it in a way where if you have some familiarity with Solidity, that's great, because most of these concepts are kind of easy mappings from Solidity to Vyper. And if you have no experience with smart contracts at all, you'll still be able to get a sense. So the first couple ones are going to go a bit slower while we cover things like setting it up and getting a basic contract. And then as we ramp up, it's going to get much more complex. If we manage to get through Unit 12, that'll be amazing because Lesson 12 is where it's like the most complex of all. Let's get started with step 1 setup. So at this point, if you're trying to follow along at home, you should do a git clone on the repository I sent. And that will get you into an environment that looks a lot like this. I hope you can see my screen. I can't actually, maybe if I pop this out, I can see for my sake if I'm getting this. Yeah, it looks like my screen is showing. That's good. So it's not quite the same because I have like a few parallel notebooks in here, but just the basic important folders here is there's a contracts folder, which is where we're going to be doing the bulk of our work. There's a scripts folder where you are going to have a couple of scripts that we're going to run in this unit here just to show off how things work, and a tests folder, which will show off essentially just how testing is done within the within this Vyper universe. So if you haven't yet, take a moment to do a git clone. And you're probably going to want to work within a virtual environment. So do virtual env. I've called mine Vyper-env. You'll press enter on that. And then once you're in your virtual environment, you can basically run pip install -r requirements.in is the file that will just have the basic requirements that we're going to be looking over. If you'd like to get mine, I did a pip freeze to this requirements.txt. But the requirements are pretty simple. We're going to be working with Vyper version 4.1, which is the latest version. I'll even drop some alpha on what's coming in Vyper 4.2 if we get far enough. We'll be using Titanoboa, which is a sort of Swiss Army knife for Vyper, and we'll be using Web3, as well as I'll show off a couple of the styling tools, Mamushi and Rough. So with that being said, this is the slide for what we're going to be covering in this first step of 12, which is we're actually, by the end of this step, going to launch a dummy ERC20 token. What we mean by a dummy ERC20 token is it's going to be an ERC20 token that's very easy. It doesn't have any like baseline requirements. It's works out of the box. It's configurable as much as you want if you use Vyper. And we're going to be able to launch it directly to Berachain. In doing so, we're going to show off how to use Titanoboa, Snekmate, CurveLite, PyTest, Mamushi, and Rough. All of these are going to be useful throughout this entire 12-step process. So to start, as mentioned, if you are installing Vyper out of the box, I was showing you the instructions where you're going to install within your virtual env by doing a pip install, which will cover everything. One nice thing about all the libraries that we use is that they are Pythonic, so you can generally install them using pip install Vyper. You can also install different versions of Vyper if you need to, as well as once you have the Vyper compiler installed, type Vyper -- version to see which version you are running. So that's a perfect sanity check. For example, here I'm not using it. Once I act my virtual environment, I'm using the latest build of Vyper 4.1. So Vyper is a super cool tool when you have Vyper installed on the command line. You can also type Vyper help to get a sense of everything you can do with it. Mostly it's just going to be a compiler, and it's going to be running within some of these other tools, but in some cases, such as extracting some contract interfaces and extracting what you would use to, for example, upload things to Berachain, it can be very useful. I also have us installing Titanoboa. Titanoboa is sort of similar in a lot of ways to Foundry, in that it's like this advanced Swiss Army knife of tools that you can use when you're coding within Vyper. This is just a simple Python import, so you'll import Boa. And when you have that, you will have a lot of really powerful tools. We're barely going to scratch the surface of what could be done with Titanoboa in this, but we will show off some of the cool features that when you get your Titanoboa installed, you can start running. There's really cool gas line-by-line debugging features. There is some IPython integration, which we will get to show off, so you can actually use this with Jupyter Labs. It allows for more seamless work with legacy Vyper versions. So when you're using Titanoboa, like there's some advanced features. It doesn't play well with Solidity. So once you start using Titanoboa with Vyper contracts and you realize some of the powerful tools you have available, you're going to say, man, I wish I could have this for Solidity, and maybe you will take the Vyper pill. Setting up Titanoboa is also very easy. You can use pip. They also have poetry and UV. I think the poetry is usually the recommended installation, but for this, if you're working in the virtual environment, you don't need to run this because it was covered by the install file. One of the other things that we want to point your attention to is the SnekMate repository. So you can get the link for this in the GitHub repository that I sent, as well as in the slide deck. If you go forward a few slides, there's a link to the SnekMate repository. Within Solidity programming, of course, one of the things that made smart contracts take off was OpenZeppelin. OpenZeppelin has an amazing amount of like pre-built templates, which you could just download and use, and they generally work. And you usually want to be careful to understand, what's going on. Otherwise, you tend to get hacked. So it goes. If you're using SnekMate, it's essentially the similar suite with Vyper. So let me go ahead and show off what SnekMate looks like here in the GitHub repository. It's got a variety of tools, many of which have actually undergone audit. So if you are able to reuse a lot of this code, this makes your life a lot easier because, of course, audits are expensive and time-consuming, but certain modules within here have actually received audits. So if you use them out of the box, they work great. So you'll find a variety of token templates. We're going to use one of them in just a minute, as well as a lot of imports, which you can use for a lot of common math, as well as other important features. The ownable one's super useful because it allows you to make contracts ownable. A lot of this is new to Vyper 4. Before Vyper 4, there was not even a modular import system. You would basically just have to install things or put everything in one single flat contract. The reason for this was many, but the Vyper team would want to be very careful with imports because if you look on, for example, like Etherscan at Solidity contracts, oftentimes they're using 15 different imports, and it can be very tough to kind of look through 15 different files. So they want to be very careful and considered in how they actually got the imports working because the Vyper team is all like very big, like readability nerds. So I didn't include this in the pip install because I was just going to do a git clone directly, which you can do as well. So git clone. Oh, I already did it. But if you type git clone and then this link to github.com/PCA/Versaccio/snekmate.git, you're going to have all these templates right here sitting in this local SnekMate directory. And this is what I was using for our actual launch of a token, which we're going to show off in just a second. So when you're dealing with the SnekMate directories, all the imports within it work directly. For the sake of this and the tokens we're going to be coding, I actually took a lot of the imports that were built into this and I structured them into the imports and interfaces folders. So a lot of the SnekMate libraries, I just cleaned up the imports and put here to keep things concise and simple and readable. So this is why you're going to want to clone the GitHub repository here when you're working with this. All right, let's hop back over. So SnekMate install, as mentioned, pretty simple. You can also do a pip install SnekMate, and then the advantage of doing that is you can import SnekMate directly. You can also install using Foundry, which is a very nice feature. The other aspect of setup here is that when we're building our lending-based stablecoin throughout this unit, we are going to need a price oracle. So for this, we're using Curve Lite, aka Curve Core. This is a pretty cool library that's built out. Full disclosure, if you missed it earlier, like I'm a Curve maximalist. I work with Curve. I'm a big Curve fan. And I'm very used to working with a lot of Curve contracts for things like setting up simple pools where you can trade tokens. And I wanted to have like a deployment of Curve that I could work with. So Curve created this repository called Curve Lite or Curve Core. And it allows anybody to permissionlessly deploy a Curve instance to the chain. So I went ahead and I deployed this to Berachain. Berachain, of course, the Berachain testnet, so that I could work with the Curve minimal smart contracts. What's nice about this is you can actually work with the team and you can get this directly onto the Curve UI. So it's missing a few of the kind of key features of like a full curve integration. Like you're not going to have all the fancy charts, but you can actually work to submit your artifacts from deployment and have it listed on the Curve UI as a kind of stripped down version. This gives you access to some of Curve's classic crypto swap, stable swap. This allows you to trade variable or fixed price tokens with each other, as well as a lot of governance features and the registries. So if you're interested in Curve on any chain, for example, Berachain or others, like you can use the Curve core as a baseline. So feel free to ping me or ping anyone on the Curve team, and we can talk a lot more through the Curve core smart contracts. When I ran the deployment, it was not difficult. It was a little costly because there was something going on Berachain, so gas was spiked to like 45. So I needed to get through a couple testnet ETH to get this deployed, but here's a sample of what it looks like when you run it. It ran super swift, and it was done in about less than 5 minutes. We got everything going, and we're going to use some of the Curve-like contracts for launching pools, which we'll show off in just a minute. Another cool tool, which one of the reasons that I really like using Titanoboa and Vyper is because it's natively Pythonic. PyTest is a really great library for testing, and building out and within whether you're using Solidity or Vyper, like building out robust testing, I think is super critical, super underrated. I think it's just best practice whenever you're dealing with smart contracts to include a PyTest or like a testing suite, so that you can actually like include that in your repository. Anyone can download it. For one, it lets devs look through the tests to get a sense what's going on. And for another, it's like super useful because they can run the tests, make sure everything's running as functions, see if there's full test coverage, and see what the developers are thinking of and what they're not thinking of. So Curve always includes tests within its repositories, and it tries to get to 100% coverage wherever possible. So we'll show off within the repository. We do in fact have a very basic testing suite we can work from, which you can just run PyTest, and you can see that everything passes because there's just one dummy test in there. We can show off a bit more as we go through and get into code how PyTest works. Two other tools that are included in the install. One is Mamushi. Mamushi is a fork of Black, but it's focused on Vyper. It is usually used within GitHub pre-commit hooks to allow the code to actually look beautiful before it gets posted. So recommend to install Mamushi. All you need to do is type Mamushi and the target, and it will nicely format the contracts for you. So if I type Mamushi contracts, it's going to take a look, and it's going to format everything, make it look nice and beautiful, and pop out, in this case unchanged because I already ran it. It allows you to just type and work and not have to do any worry about formatting until the end. Similar is Rough. Rough is a Rust tool that works as a Python code linter and formatter. So install these tools. This Rough combines basically Flake 8 and isort. So your two of the other like super useful linting tools get rolled up into Rough. So that's a lot. Here is the slides I promised you that talk through and show off all the links to all of these. So if you missed all of these, you can click through, go back and find the presentation, and you can see all the various tools that we added here, as well as a few links, which I thought might be useful. Vyper is a style guide. We'll try and like talk through some of the principles. I'll probably violate some because I'm trying to live code and talk at the same time. So you can follow along and call me out if you like, as well as the Curve is working on a style guide as well, as far as how repositories should be used. I just bring this up because it's like my particular bias in terms of how code should be styled, but there's a lot of other ones. Another super useful resource to shout out, which we're not touching in this unit, but instead of or in addition to Titanoboa, Ape Framework is also super useful at being able to like create a nice development environment that you can work with. They fully support Vyper, and they have a lot of great educational tools. So if you're looking at doing any further smart contract programming, definitely recommend to check out their ApeWorks Academy, as well as all the cool tools that they have going on at ApeWork. Another tool that you should be aware of is Moccasin. So Ape came out because there was this former like tool that people used called Brownie, which was essentially like an all-in-one Pythonic framework. It stopped seeing development, so Ape kind of was inspired by what Brownie was doing and launched a fork of Brownie and went off in its own direction. And then Moccasin is another one by Patrick Collins of Cifrin, which is trying to like be similar but provide a more Brownie-like experience. I forgot to include in the links, but just you can search for Cifrin Moccasin, another cool tool. All right, so everything should be set up. And if we are in good shape, then we should basically have like essentially like, as I mentioned, like this basic structure, like a contract, a script, and tests. So for sitting through this like massive like amount of exposition, I wanted to move to 2 of the scripts that were included. Now, in most cases, the scripts are usually Python files, but because one of the cool features of Titanoboa is that it works natively with Jupyter Notebooks, and because Jupyter Notebooks are like more fun and more visual, I thought it'd be cool to show off how we can deploy a token using Titanoboa. So you should be able to open these scripts if you have Jupyter Labs. If not, just pip install Jupyter and then type Jupyter Notebook or Jupyter Labs. In order to use Boa, you might also need to type the command Jupyter Lab extension Boa. Some of the versions of Jupyter, depending on the install, might not requirement. I typed this in the chat, and I'll type it again, formatted like code. So if it's demanding you run that, then you can run that. But this is like a super simple way of kind of loading and deploying a token. So as long as the token.vy, if I was smart and actually included it in the contracts folder, yeah, it's sitting there. The token is the flattened version of that SnekMate file token that I'd described before. So because it's very comprehensive, this token file is much more complicated version of Vyper than we're going to be actually getting to within this tutorial. But it is essentially out-of-the-box ready token that you can use and you can just deploy directly. So when you're using Boa, assuming you got your installs correctly and you could just run import Boa, I'm tossing this filter warnings in there because some versions of Boa are giving some warnings we don't need. And then when you are working with Boa, you can set up a few different environments. So for example, if you wanted to run a forked version of Berachain, you could point to that. If you do boa.set browser environment, that's just going to connect with whatever browser wallet you're using. I'm using Rabby. And then I'm passing boa.env.set chain ID to force it onto Berachain testnet. And this is going to think, and it should pop up. Of course, it's not. It should pop up a Rabby like request, and I knew this is going to happen. And it's hung. So let me try and refresh my Jupyter Notebook while it's doing this. Jupyter Notebook. See if this works any better. Take 2. Start. And just in case this happened, I had a backup one that might work better. It's okay. It's not going to play nicely. All right. So it should work nicely at home where you can run this and you can, yeah, it's not going to play nice with me today. So I will just set it to fork mode, see if that works a little better. So I'm going to launch this on a forked copy of the Bearachain, and hopefully it works better for you. And if you get this first cell running properly, then the next step is you're going to import the contract. So this is one level up in the contracts folder, the token.vy we showed off. You're going to pass it the constructor values, which is name, symbol, number of decimals, the EIP 712 name and version. And within Boa, you load it, and this gives you a contract object that you can work with. And then with this, you'll type deploy and the constructor values. There's also a load function you can use directly to do this in one step. And this is just going to now launch a token object. So now we have a token. You can see I, for example, have no amount of this token, but maybe I could run a mint on it and give myself, see how the mint function works. I could give myself boa.end for that EOA. Let's give myself 10 to the 18th tokens. And now I have enough of my token to retire off of. So as you can see, deploying meme coins, super easy. The other script in there is to actually deploy a curve pool. So this presumes that you've already got the curve core or curve lite installed. Once you've got this library installed, yeah, blame Brave. That's right. I have too much security on this. Once you got the curve core installed, then it's also just as easy to feed the addresses to it. And this is the script that you could use to launch a curve pool. In this case, it's going to be containing a ERC20 token, two ERC20 tokens, one of which is going to represent our, we'll call it just like our random meme coin that we're going to be building as the lending token, and the other is going to be the dollar token, which we're actually going to be, we're going to, the core of this unit is we'd like to create a dollar-backed lending-based stablecoin. So this is going to be basically a curve pool containing both of them that you could trade between. So basically the same deal. We are importing BOA, warnings, JSON. I'm setting it to fork mode, in which case I'm basically passing this RPC node, and thankfully Berachain is nice, and Berachain lets you fork the RPC URL. When you work against a forked version of the mainnet, it's going to basically freeze it at that block, and then you can do a lot of cool things. So testnet is kind of like no real need to fork it, but you could actually fork the live version of Berachain, assuming that the RPC node supports it. And then you could actually like spoof addresses. You could masquerade as their wallet, send tokens around, see how smart contracts are actually going to function in the wild. So this is useful because Curve doesn't generally do testnet deployments. Curve tests everything against forked mainnets because it's just it's nicer to have like the full suite of Curve infrastructure so you can see how like actual like token balances change. Let's see, fork mode is working for us. I've pasted in the addresses that I deployed to. So the factory address came from the Curve core deployment, and then the Curve address and the crvUSD address, or just two tokens I launched and deployed onto Berachain, and they're going to serve as our kind of on-chain version of our testing versions of this lending-based and stablecoin that comes out. And this is my wallet address, so feel free to go ahead and send me as many tokens as you like on any chain. No one has done that. I think the wallet address is like it's about 33 cents of value, which I kind of used to leave private keys lying around, see if anyone can find them and steal my 33 cents for it. Once again, we're loading the, that's right, pump it. There's some alpha there. We're loading the token contract. In this case, the token contract I'm just using so I can get the interface out. You need some sort of interface to be able to actually plug and play with contracts in BOA. The easiest way to do this is usually just to get the interface directly from Etherscan or the Block Explorer, where there's a built-in BOA function from Explorer. However, I was not actually able to verify some of these multi-part contracts directly on Berachain's Block Explorer. So I just am pulling the tokens directly from the interface that's generated from this token.vy. And similarly, I'm pulling the factory interface because I included the Curve core contracts within the repository just to pull out this JSON ABI object and use this to load the factory so I can interact with it. And then from here, it's just using this factory to deploy a pool. In this case, I've hard-coded two tokens as mentioned. There's a Berachain token and a crvUSD, I'm calling it. Hard-coded the price of the lending token to 69 cents. Just picked a random number out of the hat. And these parameters might look super random. If you're interested, this article here has a lot of really good information on what these parameters do. It certainly doesn't matter for what we're doing as long as the contract actually deploys. But there's one reason that if you're deploying on Curve, it's worthwhile just to ping me or anyone on the team, because we can help run a lot of tools to optimize these parameters. There's some ways you can optimize pools for stablecoin trading, or you might be able to optimize for like less volatile crypto assets like Bitcoin, or more volatile assets like if you're trying to build like foreign exchange, or if you're trying to build meme coin trading, for instance. There are different parameter sets you could use. And factory is not defined. Run the cell. So out of this, it thinks and it actually grabs a pool contract that has been deployed live. So this only exists on our forked testnet, but within this Jupyter notebook, we can look at this interface and play with the pool. So within this, we, for example, would like to see what's the curve balance and the crvUSD balance that we deployed into this pool. Now, because I've seeded it previously, it actually, this is the balance of the user that we have to fund it. So the curve and the crvUSD, the user's got like millions, it's rich. The pool's returning a price of 69 cents. To seed the pool, it's pretty easy. We take the 2 tokens, we approve them, and then we'll add liquidity to the pool. And in order to do that, we are going to seed these amounts in terms of the actual price of the crvUSD versus the curve token here. And once this is done, we actually have a pool where we can look at the balances and see that the pool, in fact, now has balances of both tokens. You can verify this by saying, what's the crvUSD balance of the pool? Or the curve balance of the pool. And because we're working right within Jupyter Notebooks, you could like maybe run some charts using matplotlib to visualize this. You could download data for use in any of the great Python data science libraries. Like, really, it's an underrated like feature of Python that has access to so many cool data science tools out of the box. So with this done, we've obviously this took a long time to get everything set up, but we have completed the first step. We have set up and been able to launch a token from scratch, just using tools that exist. From here on out, we're actually going to be coding everything. So step 2 is where we're actually going to start diving into this Vyper contract that we just barely looked at last time. And we have our token contract, but what we'd like to do is we'd like to set up a minter contract. So this token contract, we're going to kind of leave as it is. It's already been audited. It's already been tested in prod. People have used it. What we'd like to do from here is we'd like to actually like just play with a minter contract, which is going to be authorized to mint this token. So it's going to be the only contract when we're done, when we deploy this stablecoin that's capable of minting. And hence, when we're building a lending-based stablecoin, all the logic is going to be wrapped up in this minter contract. So this is what we're going to be spending most of our time working on. You'll notice in the repository, we don't have a minter contract created. We have just a Vyper Snekmate import of the token contract created. And along the way, we're going to show off the core building blocks of a minter contract, including the version pragma, how to use functions, as well as how to properly document your code. So using whatever editor you like, you can, if you're following along, you can do I'm using Vim because I'm a dinosaur and I learned Vim. I'm not starting Emacs Vim War. I like Emacs too. I just got used to Vim. So I'm going to create Vim contracts minter.vy. And I already have one. So let me just get rid of that. Call it minter back.vy. So we're all working from scratch here. And we've got a blank slate. So what we'd like to do is we'd like to get this contract to essentially just a very basic bare bones contract. No pun intended, bare bones. And what we'd like for this is for this contract to, if we're successful, just directly compile. We would like it to work when we run Vyper on it out of the box. So first thing we promised is you are going to have a version pragma. So Vyper has the very top of the Vyper contract, similar to Solidity. You just need to tell the contract what version you're using, right? Nothing super controversial there. So if you're familiar with Solidity development, like you'll also be familiar with this. When we mentioned that Vyper version 3 was the long running version up until about 6 months ago or so. Vyper 4 launched. It includes some cool features like modularization. We're not going to get too much into it. We're just going to basically say that at this point, like we're going to use the Vyper 4.1, which is the latest for all of this. And we are going to go ahead and code that into the first line of our contract here. So we have at version 0.4.1, and we have a very, very basic contracts minter.vy, which compiles. So we've actually gone ahead and written a working Vyper contract, although there's not much to it. So it's not like you should feel super proud of anything that we've done so far. Why does it think? Contracts minter.vy. Okay, there we go. Here's the right version. When you're dealing with Pragma, there's other options you could use. So with all this, like check the Vyper documentation. Everything, most of the screenshots from here on out are pulled from the Vyper documentation. You can pull it directly from there. There's some cool things you can add into Pragmas. So for example, you can say it has to be above a certain version of Vyper because they're backwards compatible. Another really cool feature is you can optimize at the Pragma level if you would care to optimize for code size or for gas. By default, it's going to be more gas efficient, which essentially means that you might pay a little bit more to compile and deploy the contract, but it's going to be cheaper to use it. If you don't care about gas, but you do care about deployment costs, you could optimize instead for minimizing code size. So this is a nice built-in feature of Vyper, which you can explore. So we have a contract, but it is not really doing a lot. It's just a empty contract. So we'd like to, from here, we'd like to actually like create a basic mint function for our minter contract. It's not going to do anything at the moment. We're just going to, so to create functions, you have to pass the contract's module scope, which means is it going to be an internal function that's only for use within the contract or external? And then from there, you're going to create a function just like within Python. So we'll mark this as external. We'll create a basic mint function, and it's not going to do anything but pass. So now if everything is working well, then when we type our minter source Vyper and bin activate, when we try and compile minter.vy, still our contract compiles, so we're in good shape. Let's make that look a little bit nicer. Let's do format interface and see that it's extracting the interface, and it now sees that there is a mint function, whereas before I added that, there is no interface when I run this. So we're in good shape. We are creating a contract that simply exists. The other final piece is, everyone likes to work within a code that is nice and pretty. Speaking of which, to optimize for code size here. We want everything to look nice and pretty. So you want to always make sure to include like nice developer documentation. And Vyper works really closely with the netspec metadata format to allow you to extract doc strings directly. So if you take the effort of actually writing your code compatible with netspec metadata, then it becomes very easy for you to like go back and create documentation after the fact, as well as it just makes developers' lives a lot nicer. There's even some compiler tools to verify that your netspec metadata is up to spec. So we're going to try our best to actually go through and add and tag everything that we're doing. So there's 2 levels of documentation. You can document like the full contract information, or you can document at the function level. These are the tags that exist and are supported by Vyper, like title, license, author, notice, and dev for the contract, as well as author, notice, dev, param, return for the function. And then you can also add custom tags for functions if you like. So this is what it's going to look like. It looks a lot nicer. Of course, in this case, the same contract basically doesn't do anything, but it's several lines of code. If you're like getting paid per line of code, it's another great free tip. So we'll go ahead and add just some like simple documentation for what we're trying to do here. We'll go ahead and say title. We'll call it the Curve stablecoin minter. We'll apply MIT license. we'll say the author is Verve Finance. Notice mint a stablecoin backed by Verve and a sample implementation of an ERC20 backed stablecoin, not for use in prod. And we will caution you, like, even though you might leave this and be like on a developer high thinking you can code anything, please don't deploy this to prod because we haven't audited this. It's probably going to lose people a lot of money. It's really a super simple, super basic like way of showing off the features of Vyper. So the hope for our mint function is that we're going to mint a quantity of stablecoins. And we're going to make a note to the developers that this function so far is intentionally not implemented. And we see this still passes. And we'll take a look at the where's our format to get the doc strings. You can see user doc and dev doc. So I'll pass Vyper dev docs to contract minter.vy. I think that's singular. And you can see that this is now passed a JSON object of everything that we had here, as well as you could do the same for user docs and get the the contracted version where it's just telling you what the functions do, and it eliminates these dev strings. So great to, don't you feel a lot better having this working here? The last thing you might want to do at this point is you could run our PyTest function to see if PyTest is working. And you'll notice that it's not actually working because the minter, the very basic test that I created doesn't actually exist at this point. But if you're being robust, you're going to want to create tests for yourself along the way. So let me just open the tests and show off how that works. I've created a large variety of tests here that we're not using all of them just yet, more just to give you a sense of what a full like PyTest conf test would look like. This is where you pass all the fixtures to your test. So these are all the objects that you're going to need to refer to frequently throughout. So in this case, for example, we're just using BOA and PyTest as our libraries. We are creating some addresses using the boa.env.generate address. This is Alice and the deployer. We're creating optional parameter you can pass to your PyTest to say if you're running these tests in fork mode or not. You are, in this case, if you're in fork mode, for example, we're going to have our stablecoin point to an actual token. If we're not, we are going to have our stablecoin point to an actual deployment. Same with the Curve token. Same with the Oracle address, because we previously deployed this. And now that we actually have a minter contract, for example, like all this is doing is this is deploying the minter contract, but it shouldn't work because it doesn't have the minter parameters. So if you're trying to keep up and you're trying to write a test to see how are we doing, we'll look at the test minter function and we'll say, okay, well, it's creating this and it's launching this, but it's trying to deploy with parameters that we don't have. So maybe if we want our test to pass, we would say just return minter.deploy. Don't pass the parameters to it. And maybe our test to see if our minter exists should just say minter. And now when we run our test, maybe it's going to pass. So we'll say, okay, cool. We are reproducing the behavior we'd like to see. The contract is actually doing what we're expecting. Life is good. And I've commented out the other versions of the test, so we can return to it later. So we're done with step 2. We might actually be able to make it through all 12 steps. I don't know how much time you all have. Any questions that we've got while we are here on step 2 before we move to step 3? All right. Feel free to shout out tests, questions throughout. Happy to answer these. If there's debugging issues, we are more than happy to do a little bit of work debugging. Mostly want to make sure you're kind of on the same page. Next up, we've got a contract. There's not much to it. So why don't we actually create like some basic token mint functionality? Why don't we actually like create a function that allows us to like mint, mint some tokens out of this? So our goal when we're done with this is to have the token mint function live and working. And again, if you are playing with this and you fall behind for anything, what you can do is you can just take a look in the contract snapshot folders where there's going to be a version of where we're supposed to be at, which you can take a look at and work with directly. All right. So our goal is going to be that there's a working token mint function by the end of this. And if you're being robust and trying to build out tests, what you would want to do at this point is you'd want to build out the test now, confirm that the test fails with the desired behavior. And then when you're done, you will run the test again and hope that it succeeds. But before we get to that, what I mean by the mint functionality is we're not actually working at the minter contract here. What we want to do is we want to get the mint function. We want to make sure that the mint function is actually minting. And to do this, I'm going to copy over Bera tutorial. Berachain tutorial contract. I'm going to pull over the token that is in the repository because I was using a different one. And this should match what you all have. If you look at the mint function here, I took the Snek-Mate version, but I actually got rid of the mint functionality so that we could run through and rebuild the mint functionality from scratch. So essentially, there is mint functionality within this, but we want to actually go through and build this out from scratch because this shows off a lot of the basic key features that we're going to be working with. It's also working with a kind of robust, super advanced version compared to our minter contract of the contract. You can see it's got all the documentation. It looks good. I just ripped it out and said to complete here. So in doing this, we're going to be able to show off the important features, basic features of how to actually interact with a smart contract in Vyper, state variables, the self object, and a few of the basic types that we're going to be using to do this. And what we would hope is that when we're done, we can call the stablecoin and actually mint on it. So why don't we just build a dummy test that hopefully fails? Easy to write code that fails, right? And then we'll call it test stablecoin can mint. We'll pass the minter. We'll pass the stablecoin. Actually, we don't even need the minter for this. We'll just pass the stablecoin to it. And we will pass, let's say Alice for now. So within this, we are going to take our stablecoin and we're going to mint Alice 10 to the 18th tokens. So we'll say Alice init equals stablecoin.balance of Alice. And then when we're done, we will assert that Alice stablecoin is greater than Alice init. And let's see if it's failing for the right reason. And indeed, it's saying Alice's balance did not increase, and that's because there's nothing in this function. So let's go through and actually complete this function here. So what's going on when we're minting? We have to have a few things change. We have to have the total supply increase, and we have to have the balance of the amount increase. And then you would ordinarily want to run some checks to make sure that not just anyone can mint, but let's just have some fun and let's create a token that anyone who finds this can mint. No restrictions, no privileges. So in order to do this, we're going to need to update the contract's storage. Of course, within Solidity and Vyper, storing internal variables is like the most important feature of contracts because you'll write a change to the contract's going to be tracking the balance of stablecoins owned by any given user. So we're going to want to actually change each person's balance as we go through and change it. Within Vyper, it looks nice and simple. It's creating a public hash map. We're going to talk about hash maps in a later unit in much more depth, I promise. But for now, just note that this is mapping in Solidity, and this is what's connecting a person's address and their balance of token. So if we're minting properly, all you need to do is change the balance from whatever you want to the new target amount. So in order to do this, we are going to read the contract, and As mentioned here, here's the documentation on state variables. So these are values that are permanently stored. They're accessible to every single contract function. To access it, you're going to use this built-in self object. If you've done any amount of Python programming, you've almost certainly seen this self object before. The self object is what basically allows you to access within the kind of overall contract object other aspects of it. We'll talk more about scoping a little bit later. So when you define a variable, you define the variable, you pass a colon to define the type. The self variable, in addition to being able to access all the state variables, it has a few other properties that it can access by default. So you can get the contract's balance of Ethereum or whatever the native stablecoin, or sorry, native gas token is. And it's used for accessing state variables. So when we want to access this balance of function, we're going to call self. So in this function, we're going to change the self balance of the owner that's being passed right here in the function. Basically, to call this mint function, we're saying who's the owner of the stablecoin that we're trying to mint for and what amount are we trying to give to them. And we will just add, using the addition operator, the amount that they are now receiving. And after this, their balance as being stored in the state variables has increased. The other thing that we'd want to do for complete this is we would want to increase the total supply. Because when you are changing the amount, you want to also simultaneously keep track of the total supply of the contract. So we're also going to say the self total supply should also be adding this amount exactly. And if we do this, then we don't need the pass function. We have a super simple but working function here. So let's also add a test for this before we write it. Let's get rid of all that. Let's test that the total supply increases as well. Stablecoin Alice init, or total supply init equals stablecoin dot total supply, stablecoin dot mint Alice 10 to the 18th. And then we'll assert that the stablecoin dot total supply is greater than supply init. And once again, we should be able to write a second failing test. 2 tests that fail, and if all goes well, when you run this, both tests should pass. And life is good. We've hit the happy path. What do you all think? Any questions? Going too fast, too slow, just right? We're going through a lot here, but we are going to have to do it if we're going to build a basically a CRV-like lending back stablecoin from scratch. Just right, nice. So I glossed over it, but that address type that we passed is native to one of the native variable types within Vyper. So the Vyper address type is holding, of course, an Ethereum address. It's nice because they look really long and complicated, and us humans can't remember it, but because it is just a hexadecimal address, it reduces nicely to an integer, so it could be stored relatively efficiently. Just note, if you're hard coding the address in Vyper, it has to be checksummed. That means that the capitalization matters. You have to have a mix of capitals and lowers. If you need a quick hack for how to do this, take that address, paste it into, for example, Etherscan or a block explorer, and they will return back that address formatted nicely and use that one. Address is nice because it has access to a lot of cool properties. You can, for example, see if that address is a contract. It comes in useful in some cases if you want to distinguish between a contract or an externally owned account. You can also get the address's balance. You can check the code hash. You can check the code size. You can even get the bytecode. So address has some cool built-in properties. The other variable type that we used here is an unsigned integer. Now, there's a lot of different integer types. There's signed integers, there's unsigned integers. You can have that be different values, anything from uint8, uint256. It gives you 2 to the whatever n you pick minus 1. In general, with Curve, they got in trouble with like flipping this around too much. It was easier for people to only work with uint256. So generally, Within Curve contracts, they mostly just use uint256. Vyper is a convert function also if you need to move between different variable types. All right, we're already on to step 4, so we might actually get through all 12 steps. We have this minting functionality, but we want to restrict it, right? Like right now we have it where anyone who finds this contract, if you deployed it, would be able to come along and mint however many tokens they like. Now, that's not the most secure, so we're going to now try and tamp this down and restrict the minting functionality just to the minter contract is the goal. So by the end of this, we're going to set up our tests so that we're only able to mint it from the minter contract. And in going through, we're going to cover a few new concepts, messages, booleans, and reverts. So first up, let me update the tests, and I'll update the test minter. Where we're going to say that this previous test that we did is fine if you are the deployer, let's say, but it shouldn't really work if you are Alice. So we will say that from 7 to 15, we'll replace Alice with deployer and say that works fine, but we'll say you can't generally mint. And we'll say, I don't really like these names. Let's say total supply, unprotected mint. And the difference here is when Alice comes along and tries to mint, it should revert. So with boa.env.revert, boa.env.revert, these should now fail if you're trying to run it. Shoot, do I have that wrong? I think it's just boa.revert. Or is it boa.reverts? I always get these mixed up. No. Boa.reverts. Yeah, so now it's complaining that it did not revert because it's unprotected, right? We need to protect this. We want a secure contract. We don't want bad people coming along. Or maybe we do. I don't know. Either way, let's go ahead and secure our smart contract. All right, so the first thing that we want to do is we want to basically confirm that whoever is sending this mint call is someone that we've actually approved for minting. So this smart contract, if you can look just a little bit below, close out this. If you look just a bit below, you can see there's already a nice set minter function, which we haven't completed yet. We'll go through and complete this as we go through this. What we want to do is we want to make sure that like only if you are like the owner of this contract are you capable of minting, and further only if you are approved by the owner, then and only then are you actually capable of going through and so only the owner can add a minter and only the minter can mint. Makes sense, right? Like that would be a pretty secure way of doing it. And as mentioned, this is using SnekMate import of ownable to check who the owner is, so we don't have to deal with any logic there. The SnekMate ownable has a few different methods you could use for what I like is the ownable two-step, where if you're assigning a new owner, you can assign it to an address, and then only when that address claims it do they receive the ownership. That way, like if you accidentally fat finger or like assign ownership to a contract that isn't capable of claiming the ownership, you still like don't lose complete access to your contract. So that's all there. All we need to do at this point is we want to check that only the owner can set the minter. So that's the other thing that we should add a test for, is we should test only owner assign minter. So we'll have the stablecoin and the deployer, and we will say that I'll call it owner can assign minter. I will say that stablecoin, and we'll add Alice as the minter here. Why not? Stablecoin. What we're going to want our test to do is we're going to want to have our test look and see if the minter where is it? Here, this is minter state variable. Alice is false to start with. And then we will have with boa.env.frank or deployer, we will have the stablecoin call set minter Alice true, and then we'll assert that the stablecoin is minter for Alice equals true. Now we run PyTest. This is going to fail yet again because we run this and this function's unprotected and doesn't do anything. So the other test that we'd want is we'd also want to test that Alice cannot come along and assign this so she's not the contract owner. So we assert that the stablecoin.owner not equal to Alice. And we'll assert that the when Alice comes along and tries to run this function, it should revert. So we'll try and use Boa's prank function to run this as Alice, and we'll try and say that this should revert if Alice comes along and tries to set the minter as herself. This is going to give me a lot more confidence that this contract is marginally secure. At the moment, why is only... Oh, I renamed this function. Test. Non-owner cannot assign minter. Okay, so now we got 3 failing. I think it should be 4. Owner can assign minter. Stablecoin cannot generally mint. Total supply and protected mint. Owner can assign minter. Oh yeah, that's right. Okay, so I think we're good. All right, now let's fix up our token. All right, we need to fix the minter set minter function. It's doing a good job of checking owner, so actually that is already nice and passing, but it's not reverting. Oh, yeah, it is reverting. Non-owner cannot assign minter. So if we only if we comment this out is this going to fail. There we go. Okay. I hadn't had all my coffee yet, but I have a feeling I was forgetting something. All right. Perfect timing to make a stable coin. 100% agree. And yeah, we're so close. We're so close. Get through a few more steps and you'll be able to launch this and capitalize on the latest narrative, which is pretty cool. All right. So the steps that we need to do. Let's make sure that the minter role is assigned properly. So we saw earlier in this contract, there's the is minter, which is again just a hash map. So just as before we were able to set the balance directly, if the owner is proper on this, then we should just be able to say, let's change is minter. Let's change the minter to the status. And then the minter is going to be fixed. And then the other thing that we'd like to do is we would like to add a check in here, which we'd just like to make sure that the minter is not the same as the message.sender. So we're going to add a check here that the minter address that we're doing this is not the same as the message.sender. For the ERC20 spec, that the minter should be the owner address, because you have to be the owner in order to send this. And what we're doing here is we're adding an assert revert string. So adding the assert statement means that this error message is going to get bubbled up. And what we could do is we could actually, within the reverts, I'll show off in a second how we can use this to confirm that it's reverting for the right reasons, that this revert string is being passed. Then the last thing that you want to do is we want to actually change this mint function to protect this here. We want to say that the self is minter. In this case, we want to make sure that the person that's sending this message is in fact authorized. So we're going to set that to true. And in order to access the parameter of who is sending this message, we're going to use this built-in Vyper message, which is just MSG. MSG.sender is the address that's calling the function, And what's cool about the message variable, built-in variable, is that it's got a lot of cool other properties you can access. So you could see how much way they're sending with the message. You could see any data that they're sending with the message. If they're sending like actual data, you can see how much gas they have. So there's a lot of reasons to use this. We are just using the message.sender type and asserting that this is in fact true. And if this works, our PyTest is not fully working. What do we do wrong? Let's take a look and see. Which one is failing here? Let's see. Test total supply increases. Oh, because we need to. Now we need to actually mint as our deployers. So with boa.env.prank deployer and with boa.env.prank deployer. Now we run PyTest and we see that our minter function is passing. We're actually getting the like basic building blocks of a working token contract. So everyone who's kept up so far, give yourselves a pat on the back. One last thing is we're comparing our message.sender to see if this is in fact true or false. This is using the Boolean type. The Boolean is another type within Vyper. If you like more information on some of the like properties of how to actually like run math using Booleans, I've dropped them here. Very similar to the Pythonic interface with Booleans. In Vyper, you can use equal statements, you can use and, you can use or. And then we showed off reverts. There's a bit more nuance we can get into in reverts. So as I mentioned, you can actually like just check when you're looking for a revert if it's actually reverting the way that you're trying to do it. So in this case, we're having Alice come along and try and mint. We could actually pass this here that she's saying the revert string should be Alice is not permitted directly. And where this test passed before, it's now going to fail because the revert string that's being passed is not the same as the revert string. But if we actually, I've been coming around to this format because it just looks nicer in Python. Of saying the revert string should just be something Pythonic like. I'm saying if it's not the minter, then that's why it should fail. So now we know that it's reverting because it's reaching this particular assert statement as opposed to reverting for some other reason, like there's maybe a bug in the code or something. The other cool thing about reverts within Vyper is dev revert reasons. So this is an object of Titanoboa. If you are trying to do reverts, and one of the debates that comes with revert air strings is that they use a lot of gas. Because you have to store strings, and strings are kind of hefty. So Boa supports dev revert reasons, which is basically saying instead of actually bubbling up an air string, just do a comment afterwards. And if my Boa is working properly, which is not, because I think I'm using an older wrong version, but if it's working properly, then this will actually pass your test without having to use the extra gas. So there's a lot of debate as to whether you should use dev revert reasons or not. I'm not going to because for one, I'm using an older version of Boa, which is broken on. But more importantly, we're on Berachain, which doesn't really like, you can get Berachain testnet tokens from a faucet pretty easily, so gas isn't really a reason. And because we're debugging, we want to make it easy for people who aren't using Boa to understand what's going on. So we're going to surface the error messages so people can see it. Just a pretty cool tool that exists within this. And as mentioned, this is more rationale for why you would want to use revert strings. Okay. So this is why my thing failed, not because I'm using the wrong version. It's because I'm using the wrong syntax here. Let's try this. Because you need to explicitly pass the dev reason. Test. No, okay. I am in fact using the wrong version. So. All right, so we will go ahead and continue not using dev revert reasons just so our PyTest can pass nicely, which it's not even doing now. Why not? Okay, because I didn't save. Get this man some coffee, am I right? All right. We're 4 steps through. I'm not seeing any questions, so we'll move on to interface. From this point, we're not going to touch our testing token. We are only going to go with our Minter contract from here on out. So you can download step 5 if you have not yet. If you got something wrong, we're only going to work with working with our Minter token, and we'd like to have it connect with. Oh, thank you for the coffee. Really appreciate that. We're going to now work on connecting our Minter with our token so that we can access it directly. And in the process, we're going to show how to extract interfaces, a few different ways to do it, how to access interfaces, and how to work with decorators. So let's close up our token here. And let's load up our minter.vy, which, as we saw, this is going to be the contract which now that we've secured our Minter contract and we can assign Minter roles, we're going to from now on want it to be the case that only this contract is capable of calling the mint function. So our goal is just that when we call the mint function through the Minter contract, it should successfully go ahead and mint the stablecoin directly. All right, so to get there, let's talk about interfaces. We saw a little bit earlier that you can extract on the Vyper command line a lot of different ways of rendering the Vyper, assuming you have a valid Vyper contract. There's 2 that you can show off here, which is, we'll run this on the contracts token. And you have to pass interface. And this is going to give you a working interface that you can use and encode as a .vyi contract to be able to pull in the interface from another contract. Or you could use the external interface, which gives you this nice compact version, which you can basically copy and paste this and drop this directly into your contract if you needed to use all these functions. Now, you only need to declare the functions you're planning on using. So for the interest of keeping the contract compact, we're only going to be looking at basically the mint function for this. But this would be a way that you could pull in everything. So if you want to pull in interfaces, like this is one easy way to do it, is you can use the Vyper on the command line to pull it, as well as the external interface you can copy and paste into a Vyper contract. The other way is you just type it directly. So when you're using the external interface, this is giving you the syntax to use within the Vyper contract to just type on a line-by-line basis the commands that you're looking to call. And then it becomes relatively trivial to pull them in directly. There's actually other easier ways you can use, which we'll show off in the next step where we're doing imports. But for the time being, let's go ahead and just create our own interface. So we'll say this is going to interface with the token contract, and we need to call the mint function. And if we do this, then we should be capable of calling this interface. So the other step that we're going to need is we're going to need to actually call this interface on an external address. So the way that you would do this is you would with every time you're referencing an external contract within Vyper, you have to pass either ext call or static call. You can see in this case, this is referencing a view function, which means you're not changing anything. So you decorate this with the static call, which is saying that we're going to access the results of this function, but we're not changing anything. So provision it that way. If it's state changing, like the mint function, you'll use the ext call interface. So you would use ext call, and then you would need to access the token interface. We would put the token address here. And then you would call the mint function, call the amount. So we'll leave this unprotected for starters. We'll say the message.sender, and the address can be minted at this address. But we're going to want to refer to this stablecoin address a lot. So real quickly before we move on, we would like to actually just hard code within the state variables of our Minter contract. Let's just, when we initialize the contract, let's assign it to a stablecoin, which means we're going to, in addition to the external and internal decorators we looked at before, We're going to use a different decorator, which is only used when you deploy the contract, that can be used to essentially set the state variables at the moment of contract creation, which is the deploy decorator. So let's create a init function to run the initialize. When you deploy the contract, similar to like a Python __ init __ kind of protected function within Python, when you're deploying a smart contract, you can, for example, set the owner of a contract, and if you have to tag it with this deploy decorator. This is going to run when you deploy the contract, and you can pass parameters to it, which would be required then parameters for successfully deploying the contract. So I'm going to create def init, and I'm going to say at initialization, we have to pass the stablecoin address, which has to be an address. And once we deploy it, let's set the stablecoin to be equal to this address. But we got to actually create the stablecoin, which will instantiate as a token. So because we declared this interface, we can declare tokens throughout. And now, instead of calling this as a token, we can just call this as self.stablecoin. So this here should bring us to everything that we need in terms of now when we deploy the contract, we have to pass the stablecoin address. But this is now going to set the stablecoin variable. And when we call the mint function, it's going to look the stablecoin variable up. It's going to know it's an external call, and it's going to mint. We haven't protected this, but this is feature complete, everything that we need. And to show off how Mamushi works, I'm not caring about linting, but I'll go ahead and run Mamushi, and it's going to reformat it, and now it looks, so much prettier. And I'm going to expect my PyTest is going to fail for various reasons at this point, mostly because the init's no longer working. I'm actually surprised as many worked as did, but it shouldn't be even capable. I'm not. I don't think my smart contract's even working, actually, now that I look at it. Let's see. Vyper contracts. I think I have a typo here. Yeah, my ext call is not calling properly. Self.stablecoin.mint message.sender. Oh, it's not the address, it's the amount. We need to pass the amount that we're minting, which will pass as a uint256, and we will record this as a param. The amount of stable coin to mint. Okay, so that's working. Now we're barely using the minter, actually, when I think about it. So there's a good reason why this is not even working. It's because the initialization is not working. But right now, funny enough, the only test that's failing is the one that interacts with the minter. So why don't I copy the tests, test minter to test stablecoin, because those are mostly stablecoin tests. So this one would be the only one we'd move to the minter, because that's the only one that actually uses the minter contract. So now our stablecoin is essentially frozen. We're not going to add any more tests there for the time being. We will get rid of all of these tests because they don't apply. So PyTest tests is now going to run through all the files, and it's going to say that most passed are stablecoins fine, but the minter is the problem. So we'll just from now on run tests on test minter. And let's go in and fix up our minter. To do so, we're going to have to fix the conf test where we're actually deploying the minter, because it's expecting deployment arguments, and we're not passing it. So if we pass stablecoin, we now see that the minter is actually working, and maybe we can go in and create a basic. Let's copy over our test that we use to assert that like Alice can mint a stablecoin, but we'll redo it to say that she's doing so through the minter, which is still unprotected, so it should be a fairly low lift. The other thing we'd like to do is when we're deploying this, before just returning the minter, I'm going to call this minter contract equals minter.deploy stablecoin. And we're going to say that the stablecoin contract now has to actually assign the minter role to we'll do that next unit because we're not actually. Oh yeah, we need to make sure that the stablecoin allows the minter contract split contracts tokens. So we'll use the set minter We will now have the deployer have minter permissions. Otherwise, this should not work. And it's not the deployer that should have the permission. It is the minter contract should now have the permission. I'll leave that there. And now not only are we asserting that the minter exists, we are going to we'll have Alice go through and go do it. Deployer is now Alice. And we're going to try and mint from the minter contract to Alice. Stablecoin, yeah. Need to change deployer here. Deployer to Alice. And what am I doing wrong? I'm encoding something wrong here, which looks like stablecoin set minter. Okay, yeah. It's the minter contract. Still bad arguments, which is minter.mint to Alice, because this mint function does not require you to say who you're minting to. It just goes to the sender. And we are failing because it reverted. It's not a minter. That is not good. Stablecoin set print minter contract. So it's printing that. Oh, because then I deploy a new one for some reason, which is not smart of me. Vyper deployer has no object mint because I need to deploy in the minter contract. All right. Now we're passing. You see why it's useful to have your tests progressively updated as you code here. All right, looking good, feeling good. I'm not seeing questions. So almost halfway through, we're going to show how we can protect the mint function now by the end of this unit. And doing so, we're going to show off a few other ways of working with interfaces here. And also, we're going to talk a bit more about the Vyper import, because as mentioned, Vyper imports are a bit new for version 4. When you're working with Vyper modules, you are essentially have a few different ways. The easiest way to work with modular Vyper is just to write a smart contract using Vyper and then import that contract. And you can import it. So in this case, showing this ownable.vy contract, which has a few functions. You can check owner, multiply, update the owner. These are various types of functions, the deployment function, a pure function, and external. Now that you've written this contract, you can be fairly flexible as to how you import it. Within Curve, the style guide recommends that if you're importing a contract, you always want to use Snek case because Vyper is Pythonic. Python uses snake case in a lot of cases. So when you're importing, it's preferable to do it as a Snek case, which is all lowercase and then underscores. If you're working with Solidity, you're probably used to camel case. You can really do as you like, just bringing that up to mention how the Curve version of it works. And that allows you to then access and use, in this case, the ownable once you've imported it. you can use many different ways. So to get the interface of the ownable contract, if you all you care about is like just pulling the token contract in, you could use the underscore interface and then call this, and now you have an ownable interface, which is being shown off here. In this case, you're calling an ownable by saying, all right, there's an ownable contract at the specific address. This inherits this interface and now has it. And this interface is usable, so you could reference it directly if you wanted to, like, you call the transfer ownership function that we built in to the ownable contract. So this allows you to import a contract and allow it to use as an interface. One other cool thing, which we're not using here, but this is useful if you're trying to like write your contracts to specs, like any ERC spec, is you can basically import an interface for like an ERC20 token. The convention that we like to follow to use that is to decorate that as an IERC20, but that'd just be a contract that shows off the necessary functions to be an ERC20 or a ERC721 NFT. And then to require that your contract actually implements it, you would pass implements and then the interface for that contract. So this is fairly short on our side. We're just going to redo our Minter contract here to, instead of using this interface imported this way, we're going to import the token contract, which is sitting in the same directory. We'll call it underscore lowercase token. And then we're also going to pull in the Ethereum ERC's IERC20, which will allow us to have an interface that works with any generic token, not just the specific stablecoin we're working with. So this means that we have a crvUSD that's just directly implementing this token. And let's imagine that our collateral token, which we're going to call, go ahead and keep this more Berachainish, BERVUSD and the BERV token. We'll call this the lending token, and we're going to say that this is just previously deployed. Maybe it's not using this exact token smart contract, so maybe the functions don't line up directly. And now we're going to, when we create this, we're going to pass the lending token address. So our lending token is now an IERC20 lending token address. And now when we're minting, we're going to go ahead and secure this function because now that we have the interfaces set, we'll run a couple of assert statements. We will check to do a static call. So we'd want to make sure that when you're minting, we want to make sure you've given allowance and approval and you actually have enough balance of the lending token to actually mint against it. So let's say that the lending token's allowance of the message sender to this contract now has to be greater than or equal to the amount that we're trying to mint for now. We'll go through the math of this later. For now, we just want to like run some basic security checks. Let's also do the same and say that the so the first one covers approval. Let's now check the balance. There's actually a few ways you could do this. You could just try and transfer the token and allow it to revert if it fails, which would be another perfectly like cromulent way of doing it. But let's add in some revert statements here. Let's say here's because you don't have approval, or here's because you don't have a sufficient balance. And other than that, when we run this now, before we actually mint the stablecoin, we're going to take the lending token away from the user by calling transfer from on it. And we will make sure that the amount is, we're just doing 1-to-1 for now. Well, like I said, we'll go through the math in a minute. Take the transfer. If it fails, then we don't bother minting. So we're going to make a few changes to our tests, no doubt. But one of the simplest is our PyTest is trying to deploy the minter without the curve address. So we will now go ahead and add the curve token address back in. And we'll just see how the tests do here at this point. It didn't even run. No, that's not what I wanted. Oh, it's because I'm not running in fork mode, and the Curve token is assuming you have to be in fork mode, I assume. Is that it? Oh, it's because I ran on conf test. Okay, so this is still failing on our Minter tests. And let's see if it's failing for what reason. First, let's check our Minter contract. I usually have some typos in here. Yeah, I do. I uppercase this when this is now supposed to be lowercase, as are you. And now token is not instantiable in storage, which is correct. This is, as I showed off here, when you're pulling in the token interface, you have to call token dot underscore underscore interface to access the interface property. And that should also mean, I believe, oops, let's make it public so anyone can see the address. This also means that we have to call the interface using the app property right here. So this is the token dot at this stablecoin address. And we also have not created, what's wrong? Lending token address has not been declared. Token address. Oh, because this is calling it address. It should be adder. No, wrong one. Now we're cooking with propane. Now it's complaining that we're not getting the right error message out. It's saying that which is accurate. We can't mint because we don't have approval. Test, minter. We just want to basically go through and say that before we can mint, we have to, first of all, assert that the Curve token balance of Alice is sufficient. We'll define the mint amount as 10 to the 18th. We'll refer to it as mint amount. Mint amount. And we're going to have to call the Curve token approval function. Call it on the minter for the, we'll give it the full mint amount. See if that helps. And I think the problem is that we actually haven't given Alice any tokens, so let's see if we can fix that. Let's just fix that in the conf test so that Alice always has some tokens. Tests, conf test. So let's say when we deploy this Curve token, in this case, we're just giving out we are giving out just a vanilla token. Token contract, we'll return the token contract, but first let's token.mint to Alice. Let's give her 1,000 times 10 to the 18th, so we never have to worry. And our token does not have a mint. Is that true? Yes, it's true because it's token contract.mint. Now it is failing because Looks like I need to encode an address. Is that right? It looks kind of, just me typing after. Now it's kind of broken it up. It's gotten everything below 100 characters. So doing good. We're halfway through. Set up this access to this Curve oracle that we created earlier. Now that we're getting more and more logic in our contract, we're going to start like separating out some of these sections here, so it's a little bit easier to see our way around. We'll come up with ERC standards at the top. We'll put our interfaces here because we're going to have a few. We'll add the state variables down here. So we are going to have to deal with a price oracle. And in this case, because we're using Curve Core, let's get the Curve Core logic back up. We're using the basic crypto swap for price oracle. Curve pools have a nice built-in price oracle function for any of the pools that you deploy. So I'll just take a kind of random pool here. All the new generation pools, make sure this is actually the newer generation pools. What they do is they use an exponential moving average of the price. So as you go along over the course of several blocks, you can actually have some assurance that it's not going to be super easy to manipulate. So it's good to work with these on chain. Now, that being said, most of the hacks that actually occur on chain have to do with price manipulation and oracles. So if you're actually dealing with oracles in real life, you want to be super careful. You want to make extra careful that you are doing your oracles properly. So please, if you're using an oracle, please get an audit. Please talk to experts before you do it. But what's nice is the pool that we deployed earlier in the smart contract actually has a built-in price oracle function, which will look something like this. Price oracle. In this case, you have to pass the argument of the token index you're talking about, but it's going to return the price based on the trading activity of the pool. So we're going to use the same price oracle in ours, and we are going to use this to figure out what the current price of our token is. So instead of just taking it one for one, because we know that the price of this token is 69 cents, as we said, we're going to actually run math and make sure that you're using the right amount. So let's go ahead and one-shot our oracle into here. In this case, because we were using a different version than the one I ended up showing on the Curve interface, the price oracle, when there's only 2 tokens, doesn't require an argument, so we don't need to pass index here. And it's going to return a uint256. You have to decorate this as a view function. And that's all that we need to actually get our oracle. Within our state variables, we will assume that we know what these are, and we'll create an oracle. And when creating these, one of the concepts we haven't talked about is within Vyper, you can actually just hard code constants. When you hard code a constant, you can use the constant keyword, and that you would set and never touch again. So in this case, constant is 1 million. You set it, and it's never going to change. And using the Vyper convention, we keep that uppercase. You can also mark it as an immutable variable, very similar to a constant. The only difference is that a immutable variable, it's assigned a value in the constructor and then never again, whereas the constant can be defined directly, not through the constructor. So there's not a huge amount of difference. There is some stuff going on under the hood as to how it modifies the runtime code. So you might, for example, if you're gas golfing, you might compare how your contracts look by assigning it runtime. Do you actually need to do that? Do you need to, is it better just to hard code it? Just for the sake of getting something in here, we'll go ahead and show what it looks like as an immutable. We'll say our Oracle function is an immutable, and it's a version of this Oracle interface. And then when we deploy, we'll go ahead and pass this as the Oracle address, which is now an immutable that gets set as we run this. So this here should compile if all is going well. Yep. Next up, we're actually going to want to use it. So our mint function isn't doing much here, but let's create a new function we're going to call an external function that is a view function. View function means it's not writing anything. And we're going to call it priceUSD, which will be just a very helpful function that exists on the contract where you can look and say, what's the current lending token Oracle price? So you have a sense of what it is when you're depositing. And it's going to return the USD price with 18 decimals of precision. And because we're going to refer to this priceUSD function both inside the contract and we might want to see it externally, I'm defining this one as external, but then I'm going to create an internal function, which is going to be able to access this. So to pull an internal function, it's as easy as calling self dot then the function name. It's kind of a convention that's not always the case, but oftentimes you'll see the internal functions are always prefixed with an underscore. So we'll go ahead and keep to that. And the nice thing about doing that is now we can just name the internal function basically the exact same thing. So I'll do internal functions here. And I'll put my external functions up here. External function. I'll just have this be deployment. So you can keep everything kind of together. Call priceUSD. It's also going to return a uint256. You can document internal functions. It's also by no means necessary. We'll skip it. The nice thing about documenting external functions is these things get bubbled up sometimes in block explorers when you're calling it. Internal functions, because they're not callable within block explorers, not necessary. Hopefully you're documenting things well. So we're going to skip that. And the priceUSD function, it's simply going to ping the static call. Static call is what you use when you call an external function of the Oracle that we defined at instantiation. And it's going to call the price Oracle function. If you're using a different type of Curve smart contract, what did we do wrong here? If you're using a different kind of Curve smart contract that used indexes, for example, you might need to hard code the index here so that you can know that, hey, this is always doing it. You might have it passed dynamically. You might need to basically just edit the Oracle function as you needed. So the problem is here, self.priceUSD. What doesn't it like about that? Cannot call a non-payable function. That's because I did not tag this properly as a view function. Here you can see the Vyper compiler really doing good work to keep your contract safe. Make sure that you're not going to inexplicably wire ETH to this function or something. All right, so as you can see, things are pretty simple. Last thing I want to mention is just scoping rules now that we have internal and external functions in our contract. This is a note. You could consult the Vyper documentation for more. We talked about how you can access via internal functions. There's also scoping for variables and modules. So certain variables are visible before they're declared. It follows the C99 scoping rules. If you got questions, you can look at this example. This here is showing off some basic properties here. It's pretty simple though. If you follow the conventions as I'm doing, you don't need to worry. On to step 8, some integer math. We have defined a price function. Let's actually get some logic for it. Let's get a getDy function, shouldn't we? I think we'll be a lot happier if we can actually calculate the amount of tokens that you would get for your loan. Which means that we're when we're creating the loan, do we actually want to let people just one-to-one get their tokens out? No, you want to figure out what's the trading rate, and you'd like to say let's give you maybe 80% collateralization. So we're going to get into some integer math here and show off how Vyper works when we're doing some higher level math. Now with CurveUSD, it's like I think it's about 90+% collateralization, but you can define it yourself based on the parameters that you have within the loan. Whereas within different stablecoins have all different things. As mentioned, this is not a real stablecoin, so don't deploy it. But as we add more and more of this math here is where it gets a bit funkier and you want to be like extra careful. Definitely, please just don't deploy this. What we'll do for the sake of this, since this is just kind of a demo, is we'll create a collateral percent. This will be a state variable, which we'll reference, and it's going to be public so you can see what the percentage is. And we're going to say that it's a uint 256 just to keep everything constant. And we're going to want to basically like hard code this. So we're going to say that like when we create this function, let's just hard code our self collateral percent to a value. So for the sake of argument, let's say we want to be 80% collateralized. There's a lot of ways that you could write this. The way I'm going to write this is to use this kind of order of operations. So I'm going to start, in this case, with the decimals 10 to the 18th, then multiply by 4. The goal here is just to get the numerator as big as possible before you do the division, because I'm always going to be doing integer division, because in this case, I'm dealing with integers. So you could, in theory, like the non-integer division operator does exist, but the compiler is going to complain because there's no decimals when you're using uint 256. So you actually want to like just go through and say, no, this has to be integer division because we're dealing with integers here. This order of operations works out the same, but it can actually work out like a little bit strange if you're like rounding off the decimal places from 4 divided by 5, the integer division of which would be 0. So in this case, the order of operations matters quite a bit here. Here we're basically just using the convention that our percentage is going to be rounded to 18 decimal places. You could change this. I've seen 10 is sometimes used. I've seen 8. Keeping it at 18 keeps it pretty consistent. So now that we have a concept of collateralization percent, let's create some get dy functions that we could use to actually use the price and see what are we getting in and out. So external view function will create again a def get dy, which is going to return a uint 256. And of course, for a get dy function, we're going to want to pass a dx, which is also a uint 256. And this will go ahead and mark up. Notice get amount of dy. In other words, how much stablecoin for a deposit of dx, aka collateral. The dx will be quantity of tokens to deposit, and it's going to return the quantity of stablecoin returned. And this will have return. This is also a function we need to refer to internally, so we'll create a parallel internal get dy function down here. Internal view def get dy to uint 256. It also needs a dx of uint 256. And in this case, the math is not too complicated. The liquidation price is uint 256. And we are also going to be running some integer division here. The math behind this is we need to get the value of what's the current price. And then we'd like to reduce this price by whatever we define the collateralization percentage as up top. And then to make the decimals match, we have to divide by 10 to the 18th. So again, we do this integer division afterwards. And then we'll return the dx times this liquidation price that we came up with. And again, to make the decimals match, we have to divide by 10 to the 18th. Let's see, that compiles, which is nice. Let's run Mamushi on this, see what it looks like. And now it looks about the same in this case. I'm not seeing what Mamushi changed, but yeah, it looks a little easier on the eyes, maybe probably some spacing. So as mentioned, we're dealing with integer math. There is integer division is pretty much what we're going to be working with. Here's the different functions you have available. There's also some like pretty cool like math libraries that have been boosted into this. So look at SnekMate for some more advanced cube root functions have been optimized, square roots, things like that. So nice thing about working with Vyper is standing on the shoulder of giants. Of course, same as Solidity, but yeah, I find it useful. One last note is that I'm working with integer division, so I basically 10 to the 18th on the last line. Thank you, Martin. Maybe I do need to start writing my tests again. Let's see how bad we're failing in fork mode now. Tests fork. Yeah, we need to clean this up pretty bad. All right, get to that in a second. Vyper does have a decimals math type. I have not yet seen it used in the wild. Most people use the convention of just multiplying times 10 to the 18th and using that for your precisions. I like that better. It works a little bit easier. If you're going to be using it, you have to pass this command line flag enable decimals, and I've played with it a bit. The returns are kind of funky to deal with because it's storing it as like this fixed point value. So I don't like it. Maybe you do. It exists. I'm just dropping this for your reference in case you do want to use it. We are like 2/3 of the way through. We're on lesson 9 here. So at this point, there's just the remaining lessons mostly just cover a few extra data types. So I'm just going to speed through each of these extra lessons, and then I'll after the fact go through and like deal with the tests, because most of these are to show off at this point. Like we've showed off all the concepts. We showed off how Curve works, how the Curve oracles interact with this. We showed off how you could trade within the Curve pools. We've showed off the Vyper types, nearly all of them. At this point, we are trying to get through essentially the last kind of types that exist within Vyper that you might need to use. So this is in turn structs, hash maps. I promise we talk about more. We're going to talk about those at the philosophical level, and events. So at this point, we are creating our loan in our lending-based stablecoin. We've passed a lot of stuff here. What we'd like to do for this unit is we'd like to actually store the properties of the loan when you create the loan. So that's what we're trying to do with the step here. And in doing so, we're gonna use the struct data type. So struct data types are pretty nice. They resemble objects within Python. So when you're using structs, it gives you access to look at and view these parameters pretty nicely. And let's see. So for our sake, we're going to be creating a loan struct, which is going to support and include all the loan properties. Within this, you can access this within your smart contract, just as you would within a Python object by using the period to access it. Vyper 4.1 is a bit stricter about how you have to actually declare the struct variables, and they're instantiated just like an object here. So let's see. Back to our code. And we will drop this up top here. We will create this and under our interfaces, let's create a spot for struct. We'll create a loan, and when you're creating a loan, we're going to want to create a few things. In the 12th lesson, which is the most ambitious one, we're actually going to go with a full crvUSD-style liquidation range to show off how that works. But for the time being, we'll do this more like a classic lending-based stablecoin where there's just a single hard liquidation price. So with crvUSD, it's got this built-in concept of liquidation protection where instead of actually getting liquidated right at the certain price of let's say 42 cents, you would say, let's spread my collateral over a band of ranges from 10 cents to 42 cents and smoothly liquidate me over that range. Because it's a tougher mental hurdle, we'll start with the classic, I just get hard liquidated at some price. So we'll actually just we'll just build this right in as the hard liquidation price when you create your loan. And we'll also need to record the deposit amount of collateral. Both of these are UINT 256s. And now we have a structure that we can work with. So we don't need to change anything else, although we are going to want to actually like record an open loan. So in the next unit, we'll actually like tie loans to specific users. For the time being, we'll just create a super like dorky contract that only allows one user to take out a loan. So we'll actually just create a state variable called an open loan, which is this struct that we just created. So structs, as mentioned here, can only be used inside of mappings and arrays. And in this case, we're just hard coding the struct as a accessible state variable here. So we don't need to actually define the struct anywhere until we create this. Let's make sure I don't have any. Yeah, this is still compiling. Let's go a little bit lower, and when we take out the loan in this mint function, we're going to actually start like storing the loan as an open loan to overwrite this variable. So we're calling it the mint function to mint our stablecoin. Now that it's getting more complicated, let's start to add some documentation. So we'll run our checks, then we'll transfer our funds. And now that we've transferred the funds, we get the money in first. Let's set the liquidation parameters. Of course, doing this last because if something, we don't want the capability of like reentrancy where you can like write this first and then re-enter. Vyper actually has a built-in reentrancy decorator which you can add to declare a function as non-reentrant. But anyway, we're not dealing with raw ETH, so it's not as much of an issue. It's just still best practice to do it in the right order. All right, so our liquidation price, we'll set a, this is just a variable that we're declaring within the scope of this function, so it's used and discarded. We're going to call our internal price USD function, and we'll multiply times the collateralization percent and divide by 10 to the 18th. This is the liquidation price that we are calculating based on this current price USD and based on how much the required collateralization percentage has been set to. Then we'll create an open loan, which is going to be this loan object. And we have to pass liquidation price and the deposit amount. All right, let's see what bugs I have here. Nope, no bugs for once. So that might be the first time I one-shotted this one all the way through. Last thing while we're here is now that we actually have a loan amount, let's reference it and let's be able to allow a user to see what their repay amount would be now that we can have this loan struct storing the loan data. Let's write a function to read the loan data from this struct. So we'll create a view function called repay amount. Again, a uint 256. We have to document this because we want it to be like clean. And let's just say get repayment amount. And if this runs properly, we'll return the amount of tokens required for repayment. Other than that, we'll call the internal function of the same name. We'll drop it at the bottom. Internal view def repay amount. Also returns a uint 256. We don't have to pass a parameter to it because this dummy contract only takes one loan. And the next unit, we're going to need to come back and redo this for a particular user because the next unit, we are going to allow this contract to support multiple loans. Return liquidation price times loan deposit amount divided by 10 to the 18th. In the spirit of don't repeat yourself code, you've noticed that we've run this mathematical operation a lot. It would probably be a good idea to do this as an internal function and just call it, shoot, what would I do? Maybe repay amount. So line 101 is complaining. Oh, yeah. fat fingered that, and we're looking good. So yeah, if I'd had more time to look over this, I probably would have created an internal function that calculated the price collateral percentage, but Curve is a company where everything's always on fire, and having extra time like that is a luxury few can afford. All right, I don't think there's any questions because conceptually it's like fairly like straightforward at this point, right? Only thing we really need to do is we need to kind of look over the as mentioned, like we're going to finalize the repay function by allowing the repay function to contain multiple user loans as opposed to just hard coding it to one user. So that's not the contract we wrote before. And instead of having just one struct, we want to have a hash map tied to a struct. This is what I was pointing at earlier when I said that structs can be defined within a hash map. You saw the sneak preview of the hash map back in, I think, step 3 when we were modifying the token contract to actually have a hash map of like things like the balance of each user. Similarly, we want this contract to support like looking at not just a single loan, but multiple open loans. So let's go ahead and do just that here. Let's it's up to, instead of a single open loan, I don't think anything eyeballing this needs to change till line 31, where instead of being able to look at the loan, we're going to change this to a hash map that points an address to a loan. So I know you've been waiting for it. I promised you I'd tell you more about hash maps. Hash maps work like Solidity mappings. They're hash tables. The way Vyper instantiates them, which I think is similar to Solidity, is that it's not like, it looks like an array in a lot of ways, but it's not an array. An array you can iterate over. That doesn't exist in Vyper. It's instantiated such that every possible key exists and every mapping exists therefore. So you're never going to, like, if you can't call an out of bounds index, every index is legally in bounds. It's just that it's instantiated with everything pointing at the default null value. Vyper doesn't really have like nulls. It has default values if it doesn't exist. So if you look up a mapping on an address you haven't defined, it's just going to return back the default value. So for our case, because we're dealing with a loan, it would be an empty loan struct. If it was pointing to uint256, it would be for example, a 0. So this is great because it's optimized for storage. It's bad because you can't just like sit there and say like, give me a list of everyone who has an open loan. You would have to say, give me a list of, you could look up, does this loan exist? Does this loan, and if so, get its parameters. But you can't iterate over it. So that's kind of like the guts of what's going on with the hash map. Other than that, you can just pull in hash maps and work with them. Hash maps have to be defined as state variables. You can't just kind of like do it as like very like randomly define one within an internal function. I haven't seen anyone ever need to do that, so I don't think that's super constrictive. Now that we've defined our open loans as a hash map, the bulk of the work is just go through every time we had open loan before and set it to look like our hash map. Before I do this, let me see what Mamushi does to our Minter contract here. So I think it's not going to like the way I have this formatted here. Yeah, it formats this onto like a line like this. All right. So instead of an open loan, we now have to set this to open loans. And the basic change here is that we're saying that you can only mint on behalf of the message.sender. You could, of course, change this. You could allow it to like pass an argument to have the sender mint it to someone else. But for simplicity, we're just going to say whoever's calling this function gets the loan. And here their loan is now set to this loan struct. So pretty simple to adjust it there. Similarly, like in the repay amount, when we are calling the repay function we created below, we mentioned that this is like going to need to be passing which loan you're trying to repay it for. So we are going to say that the repay amount we'll get for any particular address, and we'll pass this through directly to the function. repay amount. So then we'll need to change our repay amount function to work with an address. It's no longer going to look at self.openLoan. It's going to look at self.openLoans for the address that we passed. And let's see if this compiles here. Yeah, we're still compiling, so we're in good shape. So no typos so far. Let's see, what's that? Want to set up a dev team with me? Yeah, please start a dev team. If you made it this far, like I'd say that you're like Vyper experts and ready to YOLO some contracts into prod, so let's just do it. Let's create a repay function. That's the other big step that we have to do here that's missing in our contract, because if you're minting, you want the capability of repaying. The repay function is not going to take any parameters. We'll just assume there's no partial repayments to keep this simpler. Of course, crvUSD lets you repay in like much more staged amounts, but we'll say this repays the loan in full. And the dev will revert if user lacks approvals or balance for repayment. So we'll make some checks to make it a little simpler. Let's go ahead and flesh this out. So the checks we'd like to run, we'll take the user address for message.sender, just so I don't have to type message.sender every time. Or if you want to change this to in the future to repay for a user and make it simpler to run this logic. We'll first have to see if we are able to actually do this. So we'll run a check on the balance, and we'll revert and say you don't have enough balance. If not, as mentioned before, you could also just do this like simpler by trying to transfer the token, and if it doesn't transfer, that's because you obviously don't have enough balance. So we'll revert either way. This just bubbles up an error message, so it could be nicer for working with devs. We're going to check this against the repay amount function that we came up with for this user. And that's working. Other than that, next step is let's try to transfer the stablecoin. If that works, then we'll clear out the loan. And we'll finally return the user's collateral last. So to transfer the token, xcall self.stablecoin.transfer from user self, and then the repay amount. In the spirit of don't repeat yourself code, because we've hit this twice, we would probably want to actually define this up top. Go ahead and just do that and say repay amount equals that. Amount makes the code a bit more readable, makes it a little cleaner. And it's gonna clear out my OCD ever so slightly. All right, so that's gonna try and transfer the stablecoin. If that works, then we will try and clear out the loan. So we'll reference the loan as a hash mapping of open loans user. And the deposit amount is the collateral they should be receiving back. And if this, now that we've stored this in this internal quantity variable, then we will call open loans on this user and set this to an empty loan object. So that's going to look like, let Mamushi handle the formatting for us. We're going to have a loan with a liquidation price of 0 and a deposit amount of 0. As mentioned, if the parameters are, what did I do? Declare this. As mentioned, if the parameters are set to 0, that's the same thing as how Vyper recognizes it as the kind of like 0 null state. That compiles. Let's make it look a little nicer before we go on. We're not done yet. We have to return the user's collateral. They're going to complain if we don't add this line. So last step is, this is an external call, not a static call. It's just reading. An external call is writing. We'll take the lending token and we will simply transfer it from to the user in the quantity that we defined here on line 9. That Vyper and able to code a token that's similar in its like very basic principles to CurveUSD. Of course, CurveUSD's got way more complexities. Like you basically just define the parameters that it looks like. As a Vyper 4.1, you have to pass the like event parameters specifically. Yet another kind of like way Vyper is strict to make sure that you're not like inadvertently messing things up. But logging events looks like this, except it's going to be requiring you to pass the sender receiver value for this transfer function. Other than that, though, the basic event logging is just like that. If you're interested in the guts of how events work, it's pretty interesting. We're also not going to get into this, but there's like 5 different EVM opcodes for how you emit event logs. So the Vyper documentation gets into like more information on this, as well as this indexed argument, which you can pass within events. But for our sake, we just want to create a basic liquidation event that's going to fire off, which will be the user that got wrecked and the struct of the loan that they had with their parameters. So when they look up this contract and they say, hey, where did my loan go? They can look through the events and say, oh, there's me. That's what I lost. That's the state of things. All right. Not seeing any questions so far. So let's go ahead and got a lot to do to actually like get liquidations in good shape here. So the event is pretty easy, but the liquidation logic is going to require a few things. So let's add us some view functions as well as some. I usually try and keep my view functions separated from my like state modifying functions. So I'll do the same here. I'm going to create at the very bottom of our state modifying functions. I'm going to create a function that we're going to use for liquidation. This is just going to do the liquidation on a particular user. We'll say liquidate a user if token price drops into liquidation, and the param user will just define the user being liquidated. Pass for now. And we'll create a parallel view function, which is can a user be liquidated? So you might want to call this on yourself if you're at risk, for example, to know what's coming and liquidate yourself. And this is just going to the notice bubbled up to the user is going to be, is the user subject to liquidation? Param user, address of user to check, and return bool true if eligible for liquidation. And because we're referring this internally, I'm going to do this as an internal function. So we have the access to the logic elsewhere. So we'll create a parallel internal view function that defines if a user can be liquidated. So here we just think through the logic. Well, how are we going to know if a user is subject to liquidation? We need to compare the current token price. We have that stored as price USD, or rather not stored, but it's an internal function that will check the price and see if it's less than the struct that we created for that user's hash mapping. So open loans hash map to the user, use period to get their liquidation price. And I do a running check to see what I've messed up. Nothing so far. All right, so now that we have this, I'm gonna split this because I'm going to go back to the liquidate function and flush this one out. We just had this pass earlier, but now let's actually like put in the liquidate logic. The basic logic of a liquidation would be, first you want to verify the user is subject to liquidation. Then you'd want to clear out their loan data. And finally, you'd like to liquidate them. So let's first assert that the function we just created can liquidate for the user. That's returning a Boolean, so all we need to do is type in assert, otherwise not liquidation. Then we need to clear out their loan data. Since we already did this once in clearing out the loan data, it would be useful under the principle of don't repeat yourself code to create a function that actually clears out the loan data for you. So we have that earlier in here where we create the loan with the liquidation price of 0. We should now instead just be pulling this internal function for this user and repeating the code here. So this code, again, just looks at the liquidation price, looks at the deposit amount, sets them both to 0, passes a user. If I haven't messed anything up yet, yes, I have. Clear loan user. Doesn't return anything. It should, let me see. Yeah, we want to return this. So we want to where I cleared out the whole line earlier. Their loan. We want it to return the empty loan. And no, we'll go ahead and assign it. I think it's better just to go ahead and straight up assign it. So you'll just call self.clear loan and both on the user, and that's going to just directly clear it out and not return anything. So that's our repay function where we clear the loan. And similarly, it's best practice to just do them the same, running through the same. So if there's something weird in the logic or we need to change it, like maybe we're changing the struct later, it'd be better off to do it that way. Yes, that satisfies my OCD, except somewhere else we're referencing a clear loan. Oh, I didn't save it. That's probably why. Okay, compiling nicely. Let's get rid of that. All right, we have a clear loan function. Last thing we need to do is we need to actually liquidate the user. So very sad, very unfortunate, but let's say the transfer val that they're supposed to be receiving is, and we'll need to set that before we clear the loan. So we grab the transfer amount from their loan, we clear it, then we transfer that back to the user. And I'm counting on all of you to keep me honest in the code that we're typing here, because I'm just making sure it compiles. Liquidation fee, 69%. That's a really good point. Why did we set it to 80%? Let's fix that up. So instead of 80%, we'll go with 69 divided by 100. Good catch there, Socrates. We'll send you some free stablecoin from the unprotected mint version of this contract. All right, I'm satisfied. I think we are set with events. So barring any questions, we're going to go through din arrays last. In this case, like our contract's working in terms of like you could deploy this and you have a semi-working lending-based stablecoin that allows you to like basically like connect to a Curve pool, mint against it. It's not trading against the Curve pool, but it is using it for the price oracle, and you're actually able to like go through and see how everything works. So like perfect. We got a nice nice contract here. As mentioned earlier, though, like there's like two things which we're not quite done with. We haven't showed off how this concept works of DIN arrays. So that's the last concept we need to know to be fully proficient with Vyper. And then we want this to look like a little bit more like the curvUSD concept, where instead of getting liquidated at a price, which is really old fashioned, like it's such a terrible experience to have a hard insta-rect just because like a price might temporarily move down because it's liquidation, into liquidation because it's Liberation Day or something. Like markets go haywire for 5 minutes, you wake up and you're gone. It's much smoother if you like get liquidated partially. So we're not going to like fully implement the curvUSD system. We're just going to show how we modify this smart contract to use this concept of curvUSD soft liquidations. And it's a great opportunity to show off this dynamic array. So this is one of the biggest differences between Solidity and Vyper. We mentioned you can't iterate over a hash map mapping, which is kind of frustrating. One of the reasons for this is that Vyper, at least up through 4.1, is not fully Turing complete in that like you can't actually have an uncapped array. You have to define your array with a cap. And the reason for this is because like it's essentially approximating the actual constraints of the EVM. The EVM, when it's interpreting Turing complete code, it's in theory, you could have like in Solidity uncapped arrays, but there is a limit to what the EVM can actually process. So if you like your array grows in towards infinity, the EVM is not going to be capable of executing your smart contract, and it's just going to fail. So for Vyper, it's actually considered like slightly safer to declare a cap with it. Now that being said, things are changing a bit in Vyper 4.2. So I'm not going to leak too much alpha. I don't want to like harp too much on how DIN arrays work because that is going to be one of the big changes in Vyper 4.2. If you're curious to see the changes, like just look at the active GitHub history of Vyper and you'll be able to see all these things, all the discussions changing in real time. But it means like, for example, like if you wanted to have a looping over like every loan in this contract, you can't iterate over a hash map. What you could do is you could create a DIN array and say, we're going to cap, there's a maximum of 10,000 loans that this contract can support at any given time, and then use a DIN array to loop over every active loan. Like that'll be a way of doing it, is tracking at the DIN array. So this is where DIN arrays can be like, you have to like really carefully consider the construction of your contract. So like DIN arrays work pretty good if you're like doing an NFT with a max mint, for example. So we're going to use DIN arrays for the sake of our contract, just for this purpose of converting our open loans struct. We mentioned earlier that we're going to be kind of changing how this struct works. Before it's a liquidation price and a deposit amount. We're just going to change this struct from a liquidation price to a liquidation range and the deposit amount to a deposit range. So the way that the struct is going to be defined is we're going to actually call this as a DIN array. And this means that the liquidation range is no longer a uint 256. We're going to call it a DIN array over what we're going to call this new variable we're going to introduce called max bands. So within curvUSD, you can deposit anywhere between 4 to 50 bands of collateral. 4 is the riskiest because that's like the absolute narrowest. So you have a much narrower price range. 50 is really long. So we're going to create, bring it back full circle. We'll create this as a constant, not set in the deployment. We're just going to create this. We're in hard code. Max bands is going to be a constant. Uint 256 will set equal to 10 right here. Again, curvUSD, that can be dynamic. That can be between 4 and 50, which is why, don't use this contract. Use these actual curvUSD smart contracts if you really want to have a robust stablecoin. We're going to say that you're hard-coded to a range of 10. Other than that, very little else changes in our state variables. Little else changes in our init. But pretty much many other functions are going to be changing throughout our contract because we now have this concept of instead of liquidity at a single spot, there's going to be this like full liquidity distribution. So we hit this function pretty frequently. So I'm going to start by coding this liquidity distribution function, which I'll just drop at the very end of our contract. And this one's a doozy. What we're going to do with the liquidity distribution is we're going to have basically a function that's going to return a dynamic array, uint256, max bands. And what this is going to do is this is going to basically loop through your position and return a very simple dynamic max bands. Man, you can tell I'm approaching my end of talking for the day. I had like a million meetings before this, so like I didn't save my voice for this. I should have. What this function is going to do is it's going to basically loop through all the bands. It's going to see how much collateral is within that band, and it's going to return that as itself a DIN array that we can work with. So how do we do this? We are going to, within our function, we're going to need to pass to this function a quantity, uint256, and a bands, uint256. And Mamushi's going to hate this, but it'll make it look nice in the end. What we're going to do in this function is we're going to define some internal variables here. The amount per band is a uint256, which is simply equal to the quantity that we're passing divided by the number of bands. So if we're saying we need max bands, we're using 10, let's say, then we're going to pass in the quantity of collateral, and we're going to divide that fairly evenly among bands. So the total quantity we will store as just this quantity variable. The liquidate, because that's going to, or as we loop through, we might touch that. Liquidation price is uint256 equals 0. Collateral amount is nothing. Price USD, instantiate as the current price. And then a return array is this DIN array we promised up above, where we're doing 2 uint256s, and this is over the max bands, and instantiating it as an empty array. All right, so next up, now we need to loop through our liquidity distribution. This looks like for I in. When you're looping through variables in Vyper, they are strictly typing, and they are going to require that you pass the variable type in the loop. This changes from previous versions of Vyper. So if you happen to have some familiarity with Vyper, that's a new change. The way that I usually do my DIN array loops, which is also changing in Vyper 4.2, so don't get too used to this, is I just see if you're above the breakpoint, at which point we break off and stop iterating. Otherwise, we're going to set the liquidation price as price USD times the collateral percentage, which we fixed up, times I plus 1 divided by the bands divided by 10 to the 18th. So this is the liquidation price for this particular band stepping through all 10 bands. Then if the amount per band is greater than the total quantity, because we're keeping track of, we have to keep track as we go through that we're not depositing too much in any given band. And then that last band, there might be rounding issues. So if you're in that last band, then we're just going to fill this band with the total quantity and zero this out. Otherwise, we're going to distribute it evenly, which means that the collateral amount is equal to the amount per band. And from our running total, we're going to subtract out the amount per band. And then finally, our return array is going to append this particular band, which is going to be liquidation price and collateral amount. And we return the return array. Oof. Must have messed something up there. Yes, I did. Din array, if you went to max bands equals, I don't think, doesn't have a default return that has a colon at the end. Now our unknown struct argument, line 76. Yes, yes. Now it's complaining that I changed my struct. So I guess our liquidity distribution function might be working, knock on wood. Let's go through and fix up where we refer to our open loans. So this is complaining because we're calling it liquidation price. It should be a liquidation range. And of course, we're going to need to go and change this from, instead of open loans, liquidation range, liquidation price, call it deposit range, deposit price. And we call it now as a liquidation prices, we'll call it. So we're going to make a note to ourselves to fix this one up. Let's go and do it now. So before we just set the liquidation parameters, is nice and easy. This time it's going to be complicated. For our liquidation parameters, we're going to, instead of prices, we're going to have prices, another din array, uint256, max bands equals collateral amounts is another din array, uint256, max bands equals distribution is another din array, uint256, max bands. And we're going to set this equal to our new liquidity distribution function for the amount and bands. You can see now where this function comes in handy. And we're now going to go through and figure out our mint amount and everything that we need. So let's create a mint amount and start it at 0. Now let's loop through our max bands and figure out for each band what our mint amount looks like. If I is greater than or equal to the length of the distribution. Here we see we have the length function built in here, same as Python. That's going to be our cue to break. Otherwise, we'll go through and we'll append to our liquidation prices array that we created the current distribution, collateral amounts, append our other distribution, and figure out the mint amount. I0 times I1. Finally, now that we've got this nicer function here, our open loans can be defined in terms of liquidation prices and collateral amounts. And then we mint. Now that we have mint. So instead of amount, where you just passed it in, we actually calculate the mint amount divided by 10 to the 18th. So now it's going to complain hopefully about a different yes, this is complaining about a different function. And oh, this is our liquidity distribution function. So we did have a fat finger in here, and I see it. I did self underscore collateral percent, which is 69. All right. What else is going wrong here? Our distribution. I told you this 12th lesson's a doozy, and we're barely halfway through this one. The amount and bands. Our distribution should actually be self.liquidity distribution amount. think I typoed. Yeah, this is supposed to be 2 uint 256s. All right, now bands has not been declared. Where did I not declare bands? Right here. This is accurate. We need to now pass this as an argument. Or we have to hard code it. So if you want it to be dynamic bands, then you would have to pass the number of bands. I forgot that I went through and did this. You have to assert that the bands is greater than 0. Otherwise, not bands. And you have to assert that the bands is less than or equal to max bands. Otherwise, we'll pass that it is not max bands. Now it's complaining about bands has not been declared. Well, you are correct, sir. Bands uint256. And man, just give me the old Yeller treatment as I get further and further into this. You don't append plural. Oh my gosh. All right. I think everyone here is probably just laughing at me in the comments. I haven't checked in this minute. No laughter. You should be laughing at me. That's a pro tip. Return liquidation price times. Oh yeah, so this is a different function. So this is repay amount is busted. And this is accurate. Our go line 194. Our repay amount is now dealing with this old version of liquidation price. So this is strictly in this, like, let's go through and like fix all the old things that broke when we changed our loan structure. So we're still pulling the loan just the same way, but in this case, we are going to be a bit more clever about how we calculate the repay amount and actually loop through all the bands. So for I, uint 256 in range max bands. If I is greater than or equal to the length of the liquidation range, then we will break liquidation range, loan.liquidation range. Otherwise, we're just going to go through and add to this repay amount the liquidation range times the loan deposit range. Here's another one of those don't repeat yourself code things we could probably create a function for. Repay amount divided by 10 to the 18th. Let Mamushi clean that up. All right. Oh, good. We got to bingo. There's a lot of places got to fix up. Let's go knock them out one by one. Line 129, transfer value. There's no such thing as a deposit amount. You are correct. So let's go ahead and fix up our liquidation function next. So from now on, we need to fix up our transfer val. Similarly, we're just going to need to run one of these loops. Transfer val will start as 0 for I uint 256 in liquidation bands. And we'll have to create a new concept of liquidation bands right in our verification section. It's another din array. And this is going to just be calling that bands for liquidation function, which we're going to need to create for a user. Pretty sure I haven't created this one yet. And now, instead of just calling can liquidate, which is not really a concept in this new paradigm, we're going to assert that the length of the liquidation bands is greater than 0. And then let's go ahead and create our, because it's getting a bit repetitive, I will just copy the bands for liquidation function over. And drop it at the end of the contract. Same deal, create a din array, loop through, break, and And yep, haven't created that yet. All right, so liquidation is going through. It's now checking our bands for liquidation. Our liquidation function is then going to log our, we have a log at the end. I didn't log liquidation function last time. All right. User equals user, loan equals self.open loans for the user. I went to all that work to create an event and didn't use it. We're going to take our transfer val. We are going to then, before we clear out the loan, we are going to loop through our liquidation bands, and we're going to open loans, user.deposit range I, and self.open loans user. So basically, where previously we had a function to clear out the loan, in this case, we're actually just going to zero this out as we go through it. Then we are going to call the transfer function, then we'll log the liquidation function. So now that's working. I'll go ahead and get as far as clearing out the rest of these errors. Let's see, Vyper contracts minter.vy. So you can see it's mostly complaining that we haven't renamed the minter function in various places. Let's see, can liquidate is interesting, except in this new version, it's not strictly a can liquidate because we're not actually calling this internally. We're only calling it the external function. So I'll just keep the code size slimmer and get rid of this can liquidate and leave it up to users to define if there is a capability of doing that. All right, clear out the loan. I made a mistake on line 111. Get some more window space here. Because repay, I haven't fixed up the repay function. So we now want the repay function to manage the repayment. So in this case, we look at the user and let's create a new function to help out here. I'll drop this at the very end. I'm going to call it user can cover. So our check for the repay function is not going to be the same anymore. Instead of looking at this balance, we are just going to assert that the user is capable of covering whatever their repayment is. And the user can cover function, I'll go ahead and code this. It's only a few lines. Internal view def user can cover. We need the user, simple Boolean, true or false. We'll take the user balance, which is a static call of the stablecoin, access from the state variable. See if they have enough stablecoin to cover the repayment amount. Another uint 25.6. We'll get this from the repay amount function for the user, and we'll return user balance is or is not greater than the repay amount. This expression evaluates to a Boolean, so we satisfy this function here. All right, I see an unknown struct argument. That's going to be easy to squash, hopefully. The clear loan function. Now, are we using the clear loan function anymore? Yes, we are. So we'll go ahead and fix this. This is now liquidation range. It's no longer of 0. The clear loan function should now be a empty array. Same with deposit range. All right, down to repay amount is a storage variable. What did I do on line 105? I never created a repay amount in my repay function. That should be simple enough. So instead of calling repay amount, we'll use this internal function that we created for the repay amount. All right. No member deposit amount on line 108. You're right. That's now deposit range. And our repay function is no longer, in fact, we can't even get it this way. So what we want to do is we want to call, we need to calculate the deposit amount. And we're going to need a function to do that. So I'm going to create a helper function to replace this. Amount address to uint 256 loan, open loans, address, deposit amount. And here we just want to loop through the bands and figure out what their deposit amount was. Range max bands. If I is greater than length, loan amount. No. Loan liquidation range. So that's going to break if we go too far. Otherwise, we just add up the deposit amount. Loan.deposit range and return deposit amount. So now when we're asking for the deposit amount, we are just calling it for this user and setting this for this user. I think that's the final internal function we need. Basically the same function as repay amount quantity. Then we can call self.clear loan for the user. No, self.open loans.deposit. Oh. I need to call the function. All right, last line that's complaining, although probably you'll find some more. Repay amount plus equals. I must have goobered up the repay function. What did I do wrong here? Go ahead and shout if you see it before me, because I'm running on fumes. The repay amount, so we go through the loan, we grab it, we grab the repay amount, and we look at loan liquidation range. Loan underscore deposit. Oh, that was easy. It is working. So I'm not going to put you through it, but the next steps from here are ample. First off, before we would commit this, of course, we would have to send this off to auditors, all that. We have to give it a full scrub. We definitely want to run Mamushi on it. Let's clean up the formatting and see what this looks like once we get it nicely formatted. So now you can see it's like gone through. It's fixed a lot of aspects of it. Other steps we'd want to do is we stopped writing tests around 6 or 7. We would want to actually go through and write some tests, especially for some of these like extreme edge cases. Like especially that last unit where we move from a liquidation price to liquidation bands. You can see there's a lot that can go wrong. More that can go right for the user, but a lot that can go wrong on the smart contract side. So we'd want to write some pretty severe tests. One thing that's nice about PyTest is you could do hypothesis testing, which would allow you to like basically set up a bunch of like different stateful parameters and iterate over them and see how things go. A lot can happen, a lot can go wrong, a lot can go right. Other steps that you'd want to do is you'd want to refactor this contract. Like I went through pretty fast. I can already tell every time I go through this, I see more things I can fix and clean up. So I'm sure that you could shout out like 10 things I did wrong. I saw at least 5. A lot can be changed. I'm curious though, like 2070 of you are like hardcore, and now you're like amazing Vyper developers. So are there any questions I didn't cover through this? Is there anything I did you'd like me to cover? Any like lingering questions? If not, I will go ahead and point you back. This resources was dropped earlier in the chat, so you can actually go through and go back to this. All the code, at least some form of it, like I probably like goobered a bit here or there. All of it's available in stepwise piecemeal fashion in this GitHub repository, so you can check that out. If you got questions about it, this was basically built against. Oh, thank you so much, Socrates, for sharing that. I was not sure I'd be able to find that. A lot of this is built off of an earlier iteration of this, where I go through a lot of these in much slower steps on a previous version of Vyper 3. So some of the logic is different, but do check out the previous video tutorials linked in that GitHub, because you can kind of go through and like see see me go through all this in kind of real time in a lot like slower fashion. This has been the inaugural Snek-Bera-Llama workshop. Like, I hope you got a lot out of this. I like really enjoyed it. I really get to enjoy interacting with people. I hope that we're able to see something like a greater Curve deployment onto Berachain, because we showed a few of the Curve contracts, and there's a lot of cool applications you can build against a lot of this logic. Like if you can build your own, like I can think of 20 applications for Curve USD soft liquidation that could be built. Like if someone was launching a meme coin onto Berachain, like you might be able to like use the Llama markets, which is a variant of this like soft liquidation that we showed off that could be launched against any token to allow people to long or short those tokens. We could really build a lot of cool applications. So I do hope that like there's some like deeper collaboration between Curve, Vyper, and the Berachain going forward, because I think that these three animals combined might look really ugly here, but I think we could build some amazing stuff. Thank you, everybody. If you need to get in touch with me on Twitter, I am most easy, or now X, don't want to dead name it. It's easy to find Curve Cap. So just think like CAP. CURVECAP. You can find me there. I'm obviously here in this Discord. You can find me there. You can find me pretty much anywhere that like any of the Curve Discord, Telegram groups I'm lurking or actively posting. On Telegram at GERRITHALL. And I will like look forward to hearing all your comments. Thank you all.
Thank you to everybody for showing up and attending. And thank you most of all, Garrett. You're an absolute legend. It was a pleasure watching you run through everything.
Whew, it was a pleasure doing it. Although my water is empty, so I'm going to look to refill. Stick around for a few minutes if there's any questions, but I'm going to turn the camera off.
Please clap. All right, you fat fingered your stage invite, so I guess you need to
Yo,
present something now.
What's up?
Thank
So
you,
great.
guys. Thank you. Thank you, Garrett. Thank you so much for that very educational session.
Josh, are you Viper pilled?
I just joined. I missed it. I'm sorry.
This was recorded by multiple sources, so we will get that uploaded and compiled for you guys.
Great.
I will officially end the stage now by clicking the red button. Once again, thank you to all who attended, and thank you most of all to the Vyper team who supported this. We would look forward to having you guys back in the future anytime.